But I will share the screen. Okay, is my screen visible? Can anybody give a heads up?
Yes, sir.
Okay. Okay. Just a second. So, okay, I think we can start. Not many people have joined, but anyway. Okay. Okay, so we started with transformation things. So we have seen what are the how to compute the rotation matrix uh, for the case of 2D and 3D, and here we use some basic trigonometrical formula for deriving the rotation matrix, and I was showing you how to actually transform the unit vector along the axis, and so that we can have any transformation that we want. And we were also seeing homogeneous coordinates, why they are needed to add the extra dimension to define things when in the projected space, specifically when a point moves to infinity. That is not possible to handle in the Euclidean space, actually. Okay, so we have seen that this is kind of scale invariant, where many points actually in the homogeneous domain, they represent the same point in the 2D. Okay. We are also seeing 3D transformation matrices. So basically, the basic element is the same. So it's getting like for x, y, and z axis. So their positions are getting interchanged a little bit. Okay. Okay, and then we started with transformation of surface normal. Okay, how many have joined finally? Not. Okay, anyway. I think I have to take attendance if this happens next time anyway. Okay, so transformation of surface normal is a bit different than the transformation of other objects. So, so what is a surface normal? Basically, you take a cross product between two vectors in a plane. So basically, this is one plane. So this is a plane, and actually, we are trying to compute the surface normal for this plane. We take a cross product. Okay. So why surface normal is important? Because like transformation of surface normal, because let's say you are trying to do lighting in your code. So the surface normal points to this direction for this sphere, let's say, okay, in some frame, or if you are trying to do like animation or something. So in the next frame, let's say we are transforming all these elements. So transforming the light source and also transforming the object. So in that case, the surface normal will also have to be transformed properly. So if my transformed surface normal is not proper, then actually it will point to different direction, and you will get a wrong lighting calculation, and eventually you will see that the lighting is not proper at that particular position. So that's why we need to have some sort of special case for surface normal transformation. Okay. Okay. So let's take an example of why this surface normal is problematic with the non-uniform scaling. Okay. Maybe I will take this. It's okay. Okay. Let's consider a axis like this. So this is my coordinate axis. Okay. And let's say this is here is 1 and here is 2. Okay. And here is also, let's say, 1, here is 2. Okay. Okay. So now we consider a point we consider a line that is passing through 2 points. So let's consider a line passing through 2 points, like point A, which is, let's say, 0, one, 0, okay, here, and this is like this here. Okay, so this is A and this is B. Okay, so now if we take another line, So if we take another line like from the origin to point 110, so that means 110 means it will be somewhere like here, right? See, if we take a line like this, so this will be my surface normal. So this is my surface normal. Okay. Okay. So for line AB, we have a surface normal. Now we are trying to do some transformation matrix with this. Okay. So let's apply a non-uniform scaling. Okay. Because I mentioned that for the uniform scaling case and all the other cases, you can check that this doesn't hamper the surface normal calculation. This should be absolutely fine. So let's take an example of a non-uniform scaling. So let's take the matrix M is a transformation matrix. Okay. So let's take a scaling in x direction. Let's say by amount of 2. Okay. And the rest of them are 0. Okay. So 0, 1. So this is from the same scaling matrix that I defined before. Okay. 0, 0, 1, 0, 0, 0, 0, 1. Okay. So now with this transformation matrix for scaling, we will do the same. Like I will transform the line and also the surface normal, and then see where actually these things are actually going. Okay. Okay. So now let's consider the point A. So let's see where the point A is going after the scaling. Okay. So what will be A prime? A prime will be A, and we transform with the matrix this one. So what will be the result in this case? Can anybody tell? So A is 0, 1, 0, and with this one. Just multiply with this matrix.
So 0 1 0 1.
Yes. 0, 1, 0, and if we do like B prime, so P multiplied by M. So what is this?
2 0 0.
2, 0, 0, yes. Okay. So that's not a problem. Okay. And now we transform the surface normal also. So N prime is equal to N multiplied by M. So then what is this? N is going through 1, 1, 0. So that means 2, 1, 0, right? Okay. So now let's plot these and then see how things are actually looking like. Okay. So we take the same coordinate axis like this. So here is 1, here is 2. Let's say here is 1, and also here is 2. Okay. So now where is my A prime? Is 0, 1, 0. So that means here is my A prime. Okay. And B prime is 2, 0, 0. So that means like here. So this is my B prime. So notice that this has been changed. Okay. So if I draw a line like this, what will happen? It look like this. Okay. So now what happens to my surface normal? So surface normal has been transformed to 210. So 210 means where? Somewhere here. So if I draw a line like this, so this is my N prime. So is it still a normal? No, you see that actually this angle is not 90 degree at all. Whereas this was 90 degree. But this is not 90 degree. So that means it is actually violating the case for the case of non-uniform scaling. So if we have a non-uniform scaling, then actually it's not at all a surface normal. So this is not a surface normal. Okay. So that means we have to find another way to actually compute the surface normal transformation for a surface normal when it comes to the case of non-uniform scaling. Okay. But this can be done pretty efficiently. How to do this? So let's consider, uh, let's say this is your surface, and let's say this is the plane that contains a normal. Okay. And this is your surface normal. Let's call this P, and this is N. Okay. So when we transform a plane, transform the plane, So P prime is equal to, let's say M is the transformation matrix for the case of plane, okay? And let's transform the normal. Okay. So let's say this is N prime, and let's say the transformation matrix for the normal is Q, okay? We consider two different matrices for two different cases, and then see like what actually we can conclude from here. Okay. So now this is a plane and this is a normal and this is 90 degree. So what will be the value of N prime dot P prime? We take a dot product of this plane and surface normal.
0.
Yes, exactly. So this is 0. So we just write it in a little bit different way. We take a transpose of P prime is equal to 0. Okay. So now we just replace the value, okay, with this thing. So Qn transpose, and what is P? MP. Okay, there is no transpose. Okay, this is also 0. Okay, so we just take a transpose just to get a like a column and row type of thing. Okay? So we just rearrange things from here. Okay, so we can write N transpose Q transpose MP equals to 0. Okay, so now here, see, N transpose P is equal to 0. Well, because I mean we have to do something like this, right? Because this is a kind of condition, because if a normal is contained on this surface, like this plane actually, then their product should be 0, because this has to be done, because this angle should be 90 degree. So if like this is equal to 0, if and only if basically this Q transpose M is equal to 0, because this is N transpose P, so we are trying to get here. So what does it mean? So that means if you sorry, is so this is not 0, of course. This is should be I actually, right? This is I, because then basically I and multiplied by 0 is 0. Okay. So Q transpose M is equal to I means what? Q is equal to, if I do the other side, M inverse transpose. So that's basically my formula for surface normal transformation. Okay, so that means for the case of surface normal, you take the transpose of the inverse of transformation matrix, and don't do it normally that we were doing like this, multiply by the matrix, because we were having some problem with the scaling factor. But if you do this, then eventually this works pretty fine, because we see that here it doesn't have any problem. And you can take some numerical examples to check that this actually works pretty fine. Okay. So this is a typical formula for surface normal transformation for the general case, and this is different from the other transformations. Okay. Okay. So so now okay, let me see what are the things we are missing out. So these things we have discussed. So these transformation matrix ordering things, I think I discussed in the previous class last week, I guess. So here actually I was discussing with some like a composing transformation. So basically if you have a grid, and let's say all of these have like unit like length and width. So let's say if you have this type of shape and we want to transform this shape into this location. So you have to follow two steps. So first rotate by minus 90 degree. Okay. And so that means this shape comes here, and then eventually how much you have to transform. So if this point comes, this point actually comes here, so that means 1 2 units in the x direction and 1 2 3 in the y direction. So if this point then go here, so that's basically is doing here. So 2 3 0 in this direction. Okay, so this is what I was just explaining in this figure. Okay, so this is the transform normal. Anyway, it's the same thing that I discussed. Okay. Yep. Okay. So now we will see some interesting things about rotation. So this is pretty much all about the basic transformation things that you will encounter in the whole course, and even later if you work on in this area, then transformation will help in different aspects actually. So now we will see some special case of transformation. Okay. Okay. Let's take it here. Okay. So this is like a special cases of rotation. Okay. Okay. So case one. So this is a case one. Let's see how to handle these type of cases. So let's say you have an object like this. Let me draw here. Let's say this is an object. Okay. So it has a local coordinate system. Okay. Let's say this is x prime. Let's say this is y prime. Okay. Let's say this is your z prime. Okay. So I take this convention because sometimes it doesn't matter, and it depends on if you look at in the books. Sometimes they use this type of convention, so that's why I'm trying to use the same convention anyway. Okay. So this is your like a local coordinate system, okay, with the object. And let's say if your global coordinate system is something like this. So let's say this is your x, so this is your y, and this is your z. Okay. So that means a body with a like a local axis with x prime, y prime, z prime is parallel to the fixed global axis system x, y, z. Okay. So that means these my coordinate systems associated with these object is actually parallel to the coordinate system with the global coordinate system. Okay. So previously what happened? So we had a coordinate system, and if we have an object here, we were always told that rotate about theta degree around y, rotate about delta degree around x, or rotate about some other degree around z or something. But now this is basically parallel to the coordinate system, so you don't have access to here actually. So then how to do the rotation in this case, because my coordinate system here is different from the one we actually here. So basically from here actually we want to rotate the object about, let's say, any of the individual x prime or y prime or z prime. Okay. Local axis. So we have to rotate around any of these. Okay. So then how to actually solve this problem? So any idea of what should we do in this case? Any words?
So we can just shift the axis first, then rotate, and then again shift back.
Yes, very good. Actually, so what we should do is that we try to merge this, or at least move parallel to, like, coincide with one of the axes of the system, and then do the operation. And then don't forget to redo, like, undo the transformation that you were doing previously. Okay. So that means in the first case, what we should do, like, translate the body so that the local axis is coincident with the uh, coordinate axis in the same direction. Okay. So that means if we let's say we are trying to rotate around like a y-axis, so what we'll do? So in this case, so let's say this was your actually, so let's say this is your like a global system, and let's say this was your local system. So what we'll try to do is we transform it to here. So that means it will be something like this. So this is your global, and after transformation, it should do something like this. Okay, right. So that means if this axis is here, then we can now we are coincide with the like a coincident with the vertical axis. So now we can actually do the rotation operation. Okay, so the second step will be like rotate about the specified axis, right? So that means at this point, so we are here, right? So that means if we rotate here, so we do the rotation, so it will look something like this. Okay, so that's the second case. And what should be the third case? Translate back. This is very important, because if you leave it here, then actually your object was here, and after the transformation and the rotation, your object gets here. But I didn't want the transformation, like a translation, in my problem actually. So what I wanted is only the rotation part. So that means I have to undo the translation part, right? So that means at this point, basically, you uh, you take from here to here. So that means it will be like this. So now compare these two. So your axis was like this, and now it is like this. So basically, you have already done the rotation, but somewhere in between, you did some translation just because that it coincides with the vertical axis. So that's it. And this is I'm showing it for the vertical axis, where y is the vertical axis in this case. But you can do the same thing for the x-axis also. So that means if you want to coincide, sorry, if you want to rotate about x-axis, then actually you translate this x prime to x and then do the rotation and then retranslate it back here. Okay, the same thing also here. So if you want to rotate around this axis, translate it here and then do the rotation and then translate it back, right? So what will be the transformation formula in this case? So let's say x prime. So let's say let's don't consider an object. Let's consider like a vector. Okay. So x is my let's say all the point coordinates here. So x prime is the transformed coordinate. Okay. So what will be x prime? X prime will be, so x was my like a previous location or previous points, and then we do the translation. Okay, then we do the rotation in this case around y-axis, so ry, and then we do the translation inverse. That's it. So this is my, oops, what happened? Okay, so this is my formula for translation in this case. Okay, so if we try to take an example, let's see how it's going. Okay. Okay, somewhere it's getting slow anyway. Okay, so let's take an example. Okay, so let's rotate the block, so the previous block that we were considering, by theta degree about local x prime axis. Okay. Okay. Um, so okay. So how to solve this problem? So that means we are trying to rotate it by x prime. Okay. What should be the translation in this case? Right. So in this case, basically, what we have to do is, so we have to translate the block parallel to the x is equal to 0 plane, right, until the x prime axis is coincident with x-axis. So where is the case here? So actually, if we have a coordinate system like this, okay, and my object was here, right? This was my object, okay. So this was my local coordinate system, right? So and where is the x is equal to 0 plane? So x is equal to 0 plane. Okay. By the way, this should be, let's say this is negative x. This is y and this is z. Okay. So x is equal to 0 plane will be, okay, somewhere here. We consider in 3D. Okay. So there is a plane like this. Okay. So in this case, so we have to translate it about x-axis. Okay. So that means we have to translate it here. So that means we have to do the movement either like a vertical movement, because it can be somewhere at the like a top of x-axis like this, or in the like in the positive y direction, or somewhere below the x-axis. So that means towards the negative y direction. Also, you may have to move in this direction, right? So that means this will move, like if the object was here, then you move it to here. So that means from here to here actually, or if it was here, from here to here actually. So that means there are two movements. One is vertical and one is along this z-axis, like an angular kind of thing if you think it in 3D. Okay, right? So that means we have to translate by like only in these two directions, right? So what should be my translation factor in this case? How much translation do we want in this case? Can you do you have any idea of how much should we move? So let's say that the centroid of this object, this is xc, yc, zc. Okay. So then what should be my transformation or translation in this case? Any idea?
Sir, 0 minus YC minus ZC.
And why it's 0? And why is 0? Why not minus xc minus yc minus zc?
Sir, what?
Why not minus xc minus yc minus zc? Why
Sir,
0?
because we are moving parallel to x is equal to 0 plane, so xc value will not change.
Yes, exactly. So we'll move with minus 0 minus yc minus zc. Okay. So that means that's it. So this is the only required translation. Otherwise, rest of the operations are the same. So if we write the transformation matrices, so how it will look like? So T will be 1 0 0 0 because of this. Okay, 0 1 0, and this is minus YC 0 0 1 minus ZC, and with this homogeneous coordinate factor. That's it. So this is my translation. Okay, and now we have a rotation. So what was the rotation around the x-axis? So we have seen it before. This is rotation matrix around the x-axis. Okay, so this part is getting filled with cos theta sin theta factors. So that's it. So that means 1 0 0 0 0 cos theta minus sin theta 0 0 sin theta cos theta 0 0 0 0 1. Okay, and T inverse will be whatever. I think it will be like 1 0 0 0 0 1 0 0 0 1 0 0 minus yc minus zc 1. Okay, and then you plug it in the same formula here. So you just multiply all these things, and then eventually you will get x prime is equal to whatever you have. That's a result. Okay. So we did the same thing here actually. So just because we are trying to rotate around the x-axis, so that's why the x part is 0 here. Okay. So if you do the around the y-axis, then you can put the y part as well to 0, because we just need to move in these two directions. Otherwise, I mean, you don't. I mean, you can move from like here to here also actually, but that's not needed anyway. Okay. So that's how we actually do rotation in this case. Okay. So this was the case one of rotation about like, so this is basically like a parallel case actually. Okay. Okay. So this is that's I was showing. It's like this. Okay. So now let's see another case. Okay. Case number 2. So this is a bit complicated actually, and this is actually mostly used in the practical scenarios. I will show you. Okay. Let's say which color did I use for the last time? Let's use the same convention. Okay. Okay. So let's say this is your object like this. I don't know how to draw that. Okay. Let me try. Okay, whatever. And it has a, let's say, coordinate system like this: x prime, y prime. Okay, so this one actually I use it as z prime because most of the conventions that people use is z upwards for this case. So that's why I'm using it. Okay, but you can use other conventions as well. Okay, and your original coordinate system is something like this. X, y, z. Okay. So in this case, so this is basically a special case. So this is basically rotation about an arbitrary axis. So here you see that this is neither parallel nor coincident. So this is somewhere randomly in the space. Okay. And this is extremely important because in the application of robotics and animation and all these type of things, actually, this is the case you will see in most of the scenarios where actually you don't know the like what is the relation between the global coordinate system and the local coordinate system, and out of the blue you might have to transform it just like this. So this is basically mostly frequently occurs in robotics mostly, and also in animation. Because when you are moving a robot from one frame to the another frame, sometimes the coordinate axis gets jeopardized, and you might have to deal with this type of situation. Okay. Okay. So in this case, so what should be the way out? So any idea of how to actually handle this type of problem? How can we actually do this? Similar to the previous idea, you can try thinking of how should we proceed.
Sir, I think you can go towards origin. I think.
Yes, of course, because then we can coincide with the origin. Yes, okay.
Sir,
But
then
let's say if
yeah.
I go to the origin, so that means that case also this orientation is not changing, right? So we are just translating. Okay. Okay. So next. Any idea? So even if we go to the origin, but still it will look like this, right? I mean, this is, if this is in red, so it will be something like this. So somehow we have to do the coincide thing with one of the axes, right?
Sir, possibly we can rotate it to align all the axes.
Yes, actually, so let's say if we try to rotate around the z axis. So actually what we have to do, somehow this local z prime axis has to be coincident with z axis. But the problem is that this is in 3D, right? This is not in 2D. So think like how complicated is the case. So like we have to do some other type of rotations just to coincide like a z prime with z, right? Because if you try to rotate z prime to z in 3D, it's not like this possible because you don't know this angle, right? So that means you have to do like two transformations, actually two rotations. Yes, this is correct that you can move from here to here. This is the first thing we have to do, like center of mass, take the center of mass and move it to the origin. Yes, that's perfectly fine. But then actually what you have to do, you have to do two rotations. So first you take the like if I take a unit vector here, so you have to take the unit vector in the x like a yz plane. So that means here is let's say the yz plane. So if I take the vector to think it in 3D, okay? So if I take it to this plane, that's easier. We know how to do this, and then from here you can directly do this thing, transform it to here. So that means it will involve actually, and I will show in the next slides how to do that actually. But if you try to actually move from z prime to z, it is not possible because it's in 3D and you don't know the angle, like what angle actually it has like this. So what you have to do is rotate around y-axis. So that is the vector is actually going in the yz plane, and in the next step, basically, if you have it, you just move it to the z plane. So then eventually it will be coincided with the z. Okay, and then you have to do the rotation whatever you want, then undo everything what we did previously, just like the previous case. So let's see like how actually it looks like. Okay, so um, let's say assume an arbitrary axis in space. So let's assume an arbitrary axis in space passing through x0, y0, z0 with direction cosines cx, cy, cz. Okay. So direction cosines are basically the, you know about direction cosines, you have studied it before definitely, the angle between the vector and the three positive coordinate axes, right? Okay. So we want to rotate about an axis by some angle delta. So this is our task. So we want to rotate about this axis by delta. Okay, and here we consider rotation about the z-axis. Okay, that's it. Okay, so the first step, so step one. Okay, so step one. So the step one is, yes, of course, we have to do the translation to the origin. Okay, so that means translate by minus x0 minus y0 minus z0. Okay, so that it coincides with the origin. So that means we were considering like this, and so this was, so this is like a x0 y0 z0 that I was talking about. Okay, so after the transformation it will be something like this. Like this. Okay, so this is the first case, we have to do it anyway. Okay, now we have to do the second case of doing the actual rotation. Okay, okay, so let's draw the figure anyway. Let's see, maybe somewhere here. Okay. Okay, so this is let's say this is x and this is z. Okay. Okay. So this is my the OP was so this is origin. Okay. So this is let's say this is P point. Okay. Let's draw this one, this line. All right. Okay. So now project this in the XY plane. Okay. So then if I project this, so it will be something like this. Okay. And also take a projection like this one. Okay. So this is the plane. This is parallel. Okay. My drawing is not perfect, so that's why it's looking like this. And also we connect these two. All right. Okay. And consider this one as a like a plane. Okay. So let's say this is like this distance is say d. Okay. Okay. So so this is my like the vector I was talking about. So OP is basically the unit vector. Okay. So OP is like the unit vector. Okay. So what we are trying to do is so that actually OP gets coincident with the z-axis. Okay. So we have to rotate about OP. Okay. So that's what. So basically, OP is basically the axis along which we have to rotate. Okay. So that means we are trying to coincide OP with one of the known coordinate axis system. So that means in our case, so we are trying to transform OP so that it coincides with the z-axis, and then we do our required rotation and then undo everything what we want. Okay. So let's say this angle is alpha with the z-axis, right? I mean with this plane actually. So think it in 3D actually. So alpha is basically the angle between this part and the xz plane, right? Because you have to do the flipping in this direction. So the idea is that we since we cannot put it from here to the z-axis directly, so basically we will put it in the xz plane, and then from xz plane we do it put it in the directly to the z-axis. Okay. So that means in the next case basically it should be somewhere here. So this should be the first case, and in the second case we try to do it like this. Okay. So that's how we plan to do. Okay. So what were my like a direction cosines? Cx, Cy, and Cz. Okay. So that means Cx. Okay, this is 90 degree, right? But so this is 90 degree. Okay. And what is my Cx? Cx here, and Cy is here, and Cz is here. Okay. So actually, like how do we get this Cx, Cy, and Cz? So I will show you quickly like how to actually get there. Okay. So let's say this was my coordinate system. Let's say this is x, y, z. Okay. So this is OP. Okay. And we have taken projection, right? This is my projection. Well, actually, I'm drawing the same figure just for the clarity. Okay. So my direction cosine was, let's say, like what is the direction cosine? Cosine of the angle between the vector and the axis, right? So in this case, so with the P actually, so let's say this is the angle A, okay, with the of the vector, like the projection of the vector. Let's say this is P1, okay. So this is a angle between the vector and the x-axis is A, and between this and like a y-axis. So let's say this is B, and with the C actually, take it in 3D, okay, is C, okay. So we have taken a projection, and then we are trying to get to the direction cosines. Okay, so my direction cosines were Cx, Cy, and Cz, right? So what is then Cx? Cx is a cosine of the angle between the axis and the vector. So what is this? A, cos of A. Okay. So now from this geometry, how can we compute this? So just connect this part, and let's call it P2. Okay. What will be the P2 in this case? Okay, so this angle is A, and we are trying to get, this is a like a right angle triangle. So what is the cosine of A in this case? Isn't it like OP2 by OP1, right? OP2, that means this part, like the base, and what is the hypotenuse? Like OP1, this part, right? Okay, so OP2, and this one is a unit vector, right? So that means this is equal to 1, right? So that means OP2 is equal to Cx. So that means OP2 is a Cx, means this is also Cx. That's what we have written here. Okay. Okay. Similarly, Cy is equal to cos B, and we consider this triangle. So let's call it P3. Okay. So consider this triangle. Okay. And we try to write in terms of this base and hypotenuse. Okay. So this is OP3, is this one, and by OP1. So again, this OP1 is 1 because of this case. So that means this is equal to OP3. So that means OP3 is equal to Cy. So that means this will also be Cy. So that's what I have written here, Cy. Okay. And Cz equal to OP4 in the same way. Okay. So OP4, 4 is actually this one, P4. So this is Cz, means this is also Cz. So that's what I have written here. This is Cz. Okay. This is Cz. Okay. So that's how we actually get to this direction cosine like this. Okay. So what we are trying to do, again, recapitulate the things what we are trying to do. Otherwise, it might get messy. Okay. So we have an object where the axes are arbitrarily located. We don't know where in space, and there is one global coordinate system, and we want to rotate the object around one of its local axes. So let's say in our case, we want to rotate around this z prime axis, okay, by some angle delta. So in order to do this, what we have previously seen is that in order to rotate around the local axis, since we don't know the like a local coordinate system, because we know the global coordinate system well, so we have to coincide with the rotation axis with at least one of the coordinate axis in the global coordinate system. So what we did previously in the case of parallel coordinate system, where the object has a parallel coordinate system to the global system, so we translated this simply towards one of the axes, and then did the rotation and then retranslated it back. But in this case, it's not the same case, because even if we try to do the translation from here to here, actually the axes don't coincide. So that means we have to find another way of doing another sort of transformation, so that the axis, one of the axis or the rotation axis, is getting coincident with one of the axis in the global coordinate system. So that's why we have to do some special case of treatment here. So the first case we did is translate it to the origin, because this one we need it anyway. Okay, so this is pretty trivial. So in the second case, we are trying to do like two types of rotations, just to coincident the axis of rotation around which we have to transform, do the rotation. We are trying to rotate the axis so that it coincides with one of the coordinate axis system. So that means in our case, we have to do the rotation around OP, and we are trying to coincide with OZ. So that in order to do that, since we cannot do it in 3D because it's hard, because from OP to OZ you cannot go directly. So we follow two types of transformation. So first we rotate OP around x-axis by some angle, so that it gets projected in the XZ plane. Okay? And from the XZ plane, actually we rotate it again so that actually this coincides with the positive Z axis. And then actually eventually we can do the translation, do the required rotation, and that's it. Okay. So here actually I have shown a diagram where actually this OP is the unit vector, and we have projected it in the XY plane, and we are trying to get this length of these parts actually with the direction cosines in the geometrical aspect. So this part is basically Cx, Cy, and Cz, and we have seen that how actually these Cx, Cy, and Cz are coming. So Cx, Cy, Cz are the direction cosines. So that means cos of the angle between the vector and the, one of the axis in the coordinate system. So here in our case, so A was the angle between the vector like OP, or the projected version of OP, and the x-axis. So from here actually we have seen that this part is actually Cx, and that's why this is coming here. And similarly Cy and Cz. We did it because we'll need this in the calculations, okay? Because we have to rotate about alpha towards this xz then, okay? So now, so this was my step 1. So now my step 2 will be actually to do the actual rotation so that actually we get coincide with the z-axis. But I think today we are not going to start it, because if we start it, it will be too late. It's already 11:57. So maybe I think I will stop here, because otherwise I won't be able to finish it today. So we can finish these things in the next class anyway. Okay. Any question from up to here? What you want to ask anything? No. Okay. If you have any question, or any in general any question about the class or anything, if you have anything, please let me know. Okay. If not, and by the way, I have posted the assignment. Definitely, you have seen this. So it's due by 8th February. Try to do it early anyway. And the labs will start at 2, but people who cannot attend the labs, so the tutorial, they can attend the tutorial from 12. So I will close this class, and then we'll start another session. So if somebody wants to join the tutorial, you can join, but otherwise the best is to attend the lab, because that has more time span anyway. Okay. So if you don't have any other question, then thank you very much for attending, and I'll see you after a couple of minutes, some of you, in the tutorial session. Okay. Thank you very much.